Okay, so from the last video, we realized that when FD is equal to mg, FD being the drag force, that's when the point at which the parachute will continue to fall at a constant velocity. Okay, so this is the condition. What we want now is an expression for FD, and that expression is FD equals a half CD rho V squared A. Now, the CD is the drag coefficient. Rho is the density of the air in which the parachute is falling. V squared, well, when we want FD equal to mg, that V in the V squared is going to be the terminal velocity that we would require. In this case, we're going to use a terminal velocity of 8 meters per second. And A is known as the reference area, which for the case of a parachute is the area of material used. Okay, so we would like to calculate what area of material we use based on this formula and putting FD equal to mg. So let's just do that just now. So a half CD rho V squared A, V being Vt now because that's the point at which it's equal to mg, m being the mass of the can and g being the acceleration due to gravity. Okay, so we're going to put 8 meters per second in for Vt. A is really what we're looking for. Rho is the density of the air, which we take to be 1.225 kilograms per meter cubed. And CD is, well, we'll talk about CD separately on its own, but it's a constant that really the best way to calculate it is by trial and error. In a wind tunnel, it's the drag coefficient of the parachute, but there are nominal numbers out there, and for a flat hemispherical, not a hemispherical parachute, I think actually for a hexagon, that's not a hexagon at the moment, that's an octagon, but for a hexagon, CD is around 0.8, okay? There are various types of parachutes, and I will probably just go into a video later about that. You can have a hemispherical parachute, which is made from pieces of material sewn together so that it takes on an exact hemispherical shape. You can have a slightly elliptical version of that. A flat would be something like this, which is the one I'm going to do the area calculation on. And then you have a parafoil, which is something a bit more complicated, hard enough to draw, something like that you would see paragliders using. But that gives you control if you want control. Okay, so right now we're going to put those two equal and derive a value for the area that we would need to give us a terminal velocity of 8 meters per second. So multiply across by 2, so CD rho Vt squared A is equal to 2 mg, and then divide by CD rho Vt squared. So A is equal to 2 mg divided by CD rho Vt squared. Now let's put everything in. Our can, maximum weight of our can is 0.35 kilograms. That's M. G is 9.81. CD we will take for a hexagonal parachute, flat, 0.8. Rho is 1.225 and Vt squared is 8 squared. Okay, now that leads to an area of 0.10949 meters squared. All right, now we want to talk about how to work out the exact diameter for a flat hexagonal parachute. So that's the next video.